Hey IBs. All right, so we split from regular. I have 3 lessons this week. Monday, Tuesday, Wednesday. They're going to be little mini lessons. Well, I'll try and keep them under 20 minutes. And then you're going to have an assignment that's due Thursday. Now, I needed it, as it says in the lesson plan, I need it in by Thursday so I can mark it on Friday because my marks are locked on Friday. Only in like emergency situations can I take in marks after that. So what you kind of have to do is after I'm done the lesson, do the questions that are related to the lesson, and I'll highlight that in the assignment itself. Okay, so the last little bit of chemistry puts stoich and bonding together. So it's kind of like this Avengers Assemble type situation. Now, the idea of this unit is how can we double check? Like if magnesium is 2 plus and oxygen is 2 negative, like that we can prove by kind of theoretical quantum chemistry, but practically, how can we prove that we're right? So that's what this part is we can use lab analysis to help prove theoretical quantum chemistry of bonding and how things come together. Okay. So first off, I'm going to explain what an empirical formula is, and you guys are going to love an empirical formula. If you see the term empirical formula, it is the simplest ratio of any formula. So C4H10, the simplest ratio is C2H5. That's the ratio of carbons to hydrogens in the molecule. That's not the correct formula, but it's the simplest ratio. C2H4 is CH2. Yes, that doesn't exist from a bonding scenario, but in the simplest ratio, that's the empirical formula. PbO4 is PbO2. Does everybody kind of get what an empirical formula is? For example, glucose, C6H12O6, has an empirical formula of CH2O. I love empirical formulas. Now, they're really important because when we're actually going to be talking about mass spectroscopy again. Mass spectroscopy doesn't necessarily tell you the complete number of atoms in a molecule. It can tell you the ratio. So that's why the empirical formula is important. You may only have the empirical formula to go on, and you have to put the puzzle together. And I love this type of chemistry. It's called quantitative chemistry. Okay, so way more technical, and I got to grab my calculator because I can't do this in my head. Where did I put? There it is. Sorry. Man, it's been a while since I've had to use my calculator. I've been doing bonding. All right. So how do we know something like calcium chloride is actually CaCl2? All right. So we're going to do an example. It's not CaCl2, but it's a magnesium compound. So what we're going to do, what this lab is doing, is it's taking magnesium and burning it and having magnesium combine with oxygen. And then what we're going to be able to do is to figure out what the ratio of magnesium is to oxygen. Now, theoretically, it should be a 1-to-1 ratio because magnesium is 2 plus and oxygen is 2 negative. However, we can figure that out by calculations and by lab analysis. Now, it's too bad you guys are out on COVID break because we actually do this lab. You guys burn magnesium and fry it and get it crazy hot, and then we take readings from it. Okay. All right, so the little piece of magnesium was 0.05 before it was burnt, and after it was 0.084. So it got heavier. Why did it get heavier? Well, it gained oxygen, right? So the magnesium combined with oxygen, and it weighs a little bit more. As long as you don't lose it, any flex of it, it'll get a little heavier. Okay, so the mass of the magnesium that we started with was 0.05, and the mass of the oxygen that combined was 0.034. What I did was I subtracted those, and that's the oxygen that was combining to magnesium. Okay. All right. Now, to do this next part, what we have to do is find the moles of the substances. Okay. Now, we're going to use that shortcut. Number of moles is mass over molar mass. Okay. to compare these two fairly, we have to figure out the moles. So I'm going to go magnesium's here and oxygen's here. Okay, magnesium is 0.0500, and that's grams. And magnesium's molar mass is 2431 grams per mole. Okay, now that's going to get me the moles of this, 0.05 divided by 24.31. Okay, now I'm going to write out just about all of that number. It's a bit of a pain, but oh well, who cares? Okay. Now, the next one is the oxygen. Because getting ahead of myself. I'm getting kind of excited because this is a new thing. When we do this step of solving the molecular formula using this method, we use atomic oxygen's molar mass. So 16 grams per mole. Do you remember how we always double oxygen? We're not doing it in this system. We're using the exact molar mass from the table because we're using a lot of theory in quantum chemistry. So we're using just oxygen's molar mass. We're not doubling it. So that's really important. So I get 0.034 divided by 16. And I wind up with 0.002125 moles. Okay. Now the next step is I find the biggest moles, this one, and I divide it by itself. Okay, I get 1. So that means they're in the formula, there's 1 oxygen. Then I take the biggest moles and I divide it by the other substance. The other substance is moles. And guess what I get? 1.03, which works out to 1. So the ratio of these actually combining is a 1-to-1 ratio, give or take. It's actually like 1.03. It's super close. So that confirms the bonding. That confirms the ionic properties. That confirms that their ratio of charge is exact.